Let's see, I wanted to talk today initially about interpreting regression models that have interactions in them. So let me go to our notes. And I'm going to go to where we talked about the weight versus height data and incorporating an interaction into it. So weight versus height, we have our response is weight. Our main predictor is height. Now we're going to incorporate gender. And we're going to allow for there to be an interaction between height and gender. Let's write this down on the whiteboard and think about what it is telling us and how we would interpret it. So if we have response for individual I equal to this model, beta 1, let's call x height, and then we have, let me change that. I'm going to make this be capital H sub I plus beta 2 g sub I plus beta 3 h sub I times g sub I, and then random error. Okay, so a question that you would see on the exam might be, tell me what the interpretation of all the coefficients are in terms of expected values of the response. So let's think about what we have here. One way to go about figuring out the interpretation is to consider the different combinations of these predictor variables and what they give us in terms of the coefficients. For example, the expected value of y when height is 0 and gender is 0. If you plug in 0 for h and g, you're left with only the intercept. So we interpret an intercept in a regression model as the mean response when all the covariates are equal to 0. Notice that sometimes that may be a nonsensical quantity. In this case, if h is height, and these are numbers in inches maybe, we won't have any people who are 0 inches tall. So the interpretation of beta 0 would not be of importance to you in that case. What you can do alternatively in cases like that, where an intercept doesn't make sense, is, for example, we could mean center the heights. If I took all the heights and subtracted off the average of them, then a value of 0 for h would be average height. We would interpret the intercept as mean response for an average height person, gender equals 0. Let's do expected value of the response when h is 0 and g equals 1. When h is 0 and g is 1, the model turns into beta 0 plus beta 2. So that means we know how to interpret beta 2. If you take the difference between those two expectations, we can say beta 2 is the difference in means. So the mean of y, let me shorten my notation here. The mean of y when h is 0 and g is 1 minus the mean of y when h is 0 and g is 0. So beta 2, one way to interpret that is it is the gender effect when height is 0. If we didn't have the interaction term in there, that h times g beta 3, the interpretations are simpler. If there was no interaction, then beta 2 would just be the mean difference comparing g equal 1 to g equal 0. If we didn't have the interaction, then beta 2 would just be the gender effect. It's a little more complicated when we have the interaction in there. Let's keep going. Let's consider two means here. The mean of y when h is equal to, let's pick a height, call it h star, and g is equal to, let's do g equal to 0 first. And I'm going to do h equal h star plus 1 compared to h equal h star, g equals 0. For an arbitrary height, h star, let's consider the mean when h is h star and the mean when we increment h by 1 unit. The mean, according to the model for this first one, would be intercept plus beta 1 times h star plus 1. The term for beta 2 is 0 because gender is 0. The second expectation would then be beta 0 plus beta 1 h star. And if we take the difference of these two, we can interpret beta 1. Beta 1 is the difference in means corresponding to a 1 unit increase in height when gender equals 0. Or in other words, beta 1 is the height effect when among gender 0. Remember that with the interaction, what we're doing is allowing for there to be separate lines, one for each of the genders. Beta 1, beta 2 is the mean difference in genders, and because of the interaction, we have to specify when height is equal to 0. Over here, beta 1 is a mean difference in response for a 1 unit increase in h, and because of the interaction, we have to specify this is the slope for gender equals 0. And then the other piece that we need is the corresponding piece from the previous slide when gender is equal to 1. What's the expected value of y when height is some h star plus 1 and gender is 1? And let's compare that to the mean for height is just x star, g equal to 1. The first mean is beta 0 plus beta 1 times h star plus 1 plus beta 2, because gender is 1, plus beta 3 times h star plus 1 again, because gender is 1. And the second mean would be beta 0 plus beta 1 h star plus beta 2 plus beta 3 h star. We can join the constants together and say this is intercept equal to beta 0 plus beta 2, and join the slopes together similarly, like that. And then down here, we can say intercept plus slope h star. So then if we subtract those two, the intercepts cancel, and what we have is that beta 1 plus beta 3 equals this mean difference. The mean when y is, or mean of y when h is h star plus 1, and g is 1, minus the mean of y when h is just h star, and g equals 1. So beta 1 plus beta 3 is the slope for gender equal to 1. So what do I need to interpret? What's left over to interpret here? We have figured out what beta 0 is, what beta 2 is, what beta 1 is. We don't yet have a definition for beta 3, but now we can get it. If beta 1, let me say we can call beta 1 the slope in height for gender equals 0. Whereas this one, we can call the slope in height when g is equal to 1. Beta 1 is the slope for height when g is 0. Beta 1 plus beta 3 is the slope in height when g is 1. So that means that beta 3 is a difference of slopes. So I'm going to write it out in shorthand. Well, I'll write it out full and then in shorthand. So this would be the mean change in response when h increases by 1 for those in g equal 1. So here's one mean difference, h star, g equal 1. It's that minus the slope for g equal 0. Or in words, the difference in slopes. A difference of differences. Difference in slopes for height comparing g equal 1 to g equal 2. And I mentioned you can think of this as a difference of differences. So, when we have this model with an interaction, we're allowing for two separate lines. And we have now interpretation of the coefficients. Beta 0 plus beta 1 is the line in height for gender equals 0. Beta 0 plus beta 2 plus a slope of beta 1 plus beta 3 times h is the line for gender equal 1. And you can see from this expression here the relationships we just saw. If the slope, or if the intercept for g equals 0 is beta 0, we can see right here the intercept for the gender equal 1 is beta 0 plus beta 2. So beta 2 is a shift in the line when you go from gender equals 0 to 1. You can also see if the slope when gender is 1 is beta 1 plus beta 3, where the slope for gender equals 0 is just beta 1, you can see that interpretation of beta 3 that we wrote down on the whiteboard as well. Beta 3 is a difference of slopes, a difference of differences. Okay. Now let's go to the script for these data. Weight, height, data script. And let's actually fit a model with an interaction and do inference on it. Load in the data. Okay. And let's come down to inference. We already looked at the simple linear regression model that just related weight to height. Matched it manually. Let's come down to beginning line 144. This is the model that has height and gender in it. Let's see, I have height, race, and gender in this model. That's okay. We'll keep it like I have it in the script. I have height, gender, an interaction between gender and height, and I also included race. I mentioned last time that when you put race in the variable or in the model, we need to be careful to make sure that R is treating race as a categorical variable. As it's written right there, we saw last time that R will treat race as a numerical variable by default, which means it's going to try to compute a slope in race, which does not make sense. Race is coded numerically, but we want to turn those numbers into categories. I do not want to treat these 1s and 2s and 0s as numeric values. The way that we handle categorical variables in R is to translate them into factors. So race equal factor race has race set up for us now. Okay, so then here is a linear regression model that has all the terms in it, including race. Let's look at summary of that fitted object. This is the classic output that you get from a regression model. Regardless of the software you use, you'll always get this table that has, for each term, intercept beta 0, beta 1 for height. We have separate betas for 3 of the race levels. Then there's a beta for gender and a beta for interaction. These are the estimated coefficients, beta hats. These are their standard deviations. These are the ratios of estimates to standard deviations. That's appropriate if we wanted to test whether each of the coefficients equals 0. The natural test for whether the coefficients are 0 is of this form. Beta hat minus what we think it is under the null, in this case 0, divided by SD of the estimate. So if you just do estimate divided by SD, like R does, then this statistic is appropriate for testing. Is this coefficient equal to 0, yes or no? But suppose we want to ask a slightly different question. You know, we figured out what all those beta coefficients mean. So we could ask, is beta 4 equal to 0? But a more interesting question would be, is there, according to our model, is there a height effect overall? If I want to ask, is there a height effect overall, then I don't get to just look at this term right here. Because height is in the model twice, there's really two height effects. There's a slope for gender equals 0 and a slope for gender equal 1. In terms of asking, is there an overall height effect, we need to assess both of those representations in the model. So what we're going to do using likelihood ratio tests and f-tests is, instead of looking at just that height variable, we're going to consider pulling that variable and the intercept variable out. We're going to consider the null hypothesis that that coefficient and that coefficient equals 0. If both of those equal 0, then you can pull height out of the model. It is not playing a role in the model. I'm going to go ahead and run this. I think this repeats what we just did, but it also computes some things manually. Uh-huh.
So whenever you do this test, obviously you get a number, right? Do we still use 0.05 as a 16% cutoff?
So we're going to do the question was, when we do this test, we get a number, p-value, and do we compare it to a 0.05 threshold or something else? 0.05 is what we'll use. That's the most widely used threshold, I think. But we are going to do one test. That's the key. If I want to ask, is there a height effect? There's two coefficients in the model. So you could think about looking at both p-values, but that's not it's not a rigorous way of doing it. What you want to do is a single test, null hypothesis that height can be pulled out of the model. And what that looks like, I have it written down over here. So in this model, this one does not have race in it, but it does have height, gender, and interaction. If we wanted to ask, say, is there a gender effect? Same issue applies. Gender's in the model twice. Is there a gender effect would then translate to the null hypothesis that both coefficients are equal to 0. Both coefficients that involve gender are equal to 0. This is where we need likelihood ratio tests or f-tests. But it is just one test, so we'll use the usual p-value thresholds, like a 0.05. Okay. So let's do a test in the model we're playing with for whether there's a height effect. The interaction term complicates the interpretation of the model, and like I've been saying, we now have to consider two coefficients at the same time. That is not a problem for likelihood ratio tests or f-tests. Let me remind us what a likelihood ratio test looks like. To do a likelihood ratio test, what we do is fit two models. We fit the unrestricted model, which is the one that we think is the appropriate model. And then we fit the null model, which is the model where we have forced the null hypothesis to be true. In this case, the null model would be the model that does not have either of the height terms in it. So you fit two models, and then you get the maximized likelihood for the two models. Remember, a likelihood is just, roughly speaking, probability of seeing the data for a given set of parameter values. So let's compute maximum likelihood for the full model, maximum likelihood for the null model, and let's get the maximized likelihoods for both, L1 and L0. Then the test statistic we'll use is this one, -2 times the log likelihood ratio. That's why it's called a likelihood ratio test. And we'll compare it to a chi-square distribution. So let's come back over here, and I need to fit the two models. We have already fit the unrestricted model, right here we did that. So model matrix for height, gender, race, and interaction between height and gender. Then my coefficient estimates and standard deviations, all the pieces I need in order to compute a likelihood, I can compute. Beta hat, x transpose x inverse, x transpose y. Residuals are observed minus fitted values. My fitted values I'm computing as just x times beta hat. You can also get fitted values using the predict function for LM. I'll show you that at some point. Once we have residuals, we know how to estimate that residual variability, sigma squared. Here's the square root of that, which is just a sample variance of the residuals. And then the variance, covariance matrix for beta, all the betas, is sigma squared times x transpose x inverse. And we can estimate that by plugging in sigma hat for sigma. So let's just verify that we've got the right numbers here. The intercept is 13.005. Got something wrong. Let's see. Height, race, height, gender. Why am I not matching? Let's see. LM. Capital X, height, gender, race. I have the ordering different, but that shouldn't make a difference. Oh, those are, okay. The numbers at the bottom are not beta estimates. Those are standard deviation estimates. Let me print out summary of the fit. This was from LM. And then here are our manually calculated beta coefficients. They match. And inside this var beta, that will be a 7x7 matrix. And the variances of the beta hats are in the diagonal. If I say square root of the diagonal elements, these should match the standard errors or standard deviations. 13.005 for beta 0, 0.196 for height, and so on. So we have the pieces for the full model. Now let's compute the reduced model. The reduced model in this case, if I want to ask, is there a height effect, is the model just like above, except where we pulled out height. Both the main effect and the interaction are gone. So I have a new model matrix. I have a new dimensionality, number of coefficients in the model. It's just 5 now. I pulled out 2 when I pulled out height. So here are the same calculations for getting beta estimates and standard deviations. Run that. If I did summary LM weight tilde gender plus race, then these should match our manually calculated estimates and standard deviations. Square root of the diagonal of var beta 0. Those match as well. Okay, so then to do the likelihood ratio test, what we need is the actual likelihoods. We have maximum likelihood estimates. The likelihood, I need to go to the normal distribution and plug in my fitted values. What's the probability of these fitted values? And I'm using my estimated parameters in this calculation. If I ask for d norm of weight, let's go here. If I ask for d norm of my observed weight values, weight hat, the fitted values, are the means, the predicted values for each individual. My estimated residual standard deviation is sigma hat. So if I said d norm, that, it would spit out in numbers, 240 numbers, one per individual. It's the normal PDF evaluated at each individual where we're using our MLEs as the parameters. I said last time that if you try to say d norm and product all the terms, you'll have computational issues because the numbers get really small. So what is a better strategy is to, instead of product the densities, to sum the log densities. I have as an argument over here at the right, inside d norm, log equal true. That means it's going to evaluate the density, but return to me the log of it. So these two terms right here are the log maximized likelihoods, and then I can use them to compute the likelihood ratio statistic, which is -2 times a log likelihood ratio, equivalent to -2 times a difference of log likelihoods. And then a p-value could be obtained from a chi-square distribution with what we call q degrees of freedom. Let's see. We called it q degrees of freedom. And what we mean by that is how many coefficients were in the full model, how many were in the reduced model. Q should be the difference. The difference in dimensionality of the two models. Just FYI, a chi-square distribution is only for non-negative data. So chi-squares look like this, or like that, or like that, but they never go to zero. They never go below zero. Evidence against the null, because of the nature of a chi-square, will look like statistic values that are out in the extreme right tail. That means the p-value is 1 minus a CDF calculation. That's the same thing as a right tail probability. In the chi-square, with that many degrees of freedom, what's the right tail probability evaluated at our statistic? Let's compute this. We get a p-value that's near as makes no difference, 0. Really, really small p-value. Here's the output from the original model. And notice that the p-value for testing whether there's a height effect, the main effect, is tiny. And the p-value for the interaction is tiny. We are very confident that our p-value using a likelihood ratio test is going to be tiny. If the interaction is statistically significant and the main effect is statistically significant, probably both of them together are going to be statistically significant. But it is, I'll emphasize, not the right answer to just look at these two p-values. You could, for example, have both of them be not statistically significant, and yet the likelihood ratio test turns out significant because it's considering them jointly. All right. That's a likelihood ratio test. Let me also show you a similar test that we'll use sometimes called an F-test. Once we have done a likelihood ratio test, we have all the ingredients to do an F-test very easily. So there's not really any extra calculation required. And you can do an F-test without doing manual calculations. There's an easy way to do an F-test in R. I'll show you that in a second. But here's the idea of this F-test. We're still thinking in terms of those reduced and null, unreduced or unrestricted and reduced or null models. And we're going to pull out the residuals from those two model fits. So call E0, the vector, the difference between observed and fitted under the null model, and call E1 the same thing with the unrestricted model. Then the pieces that make up the F-test are sums of squares of those residuals. Residual sums of squares. Literally just add up the squares of the residuals. We have one for the null model and one for the unrestricted model. Then the F statistic is of this form. N minus P, P is the dimensionality of the full model, divided by Q, remember that Q is the difference in dimensionalities. Then we have a ratio comparing RSS0 to RSS1. And under the null hypothesis, that has an F distribution. If the data themselves are normal, then under the null hypothesis, this has an F distribution. So here's how you can do it. Just a few lines of code given what we already have. Up above, I computed, remember, beta hat and y hat response fitted values. Then the residuals, just called them EE, weight minus weight hat. Similarly, there is an EE0 for residuals from the null model. Then here are the pieces we need to do the F-test. Residual sums of squares for both of the models. And the F statistic is then what we had over in the slides, N minus P divided by Q, or N minus P0, times RSS0 minus RSS1 divided by RSS1. So I have N minus P, the difference in dimensionality, and everything else as stated. Then a p-value for an F-test. F distributions are also like chi-square in the sense that they don't go negative. So again, evidence against the null will be located in the right tail. We're looking for evidence of big positive test statistics. So here again I have right tail probability evaluated at our test statistic with the appropriate degrees of freedom. Let's run this. We get another p-value that's near as makes no difference, 0. And let me just show you how you can do those F-tests using a built-in function in R. We've talked about ANOVA a little bit. ANOVA is its own thing. It's for comparing means, 3 or more means. But there's a function called ANOVA in R that compares and does inference on nested models. Nested models are models like if we said this model up at the top and wanted to compare it to the model that does not have the height terms in it, the second model is nested within the first one in the sense that you can create the first one from the second one by just adding more terms. So they're the same. They started at the same place, but the model that's nested within the other has some of the terms removed. When you have nested models like that, if you construct LM objects like we have, fit is the result of doing LM for the full model. Here's fit 0, which is the null model according to LM. Then ANOVA, where you pass in the two fitted objects, computes that F test. We can't really compare it. Well, we could compare the F statistic. Here's the F statistic. Here's the likelihood, or I'm sorry, the F statistic that we computed manually. So it's doing the same thing. When you have nested models, you can use the ANOVA function to perform arbitrary tests on the coefficients. All right. Let me comment on this slide. Remember the pollution data where we had, I think, 4 pollution variables. There was HC potential and SO2 potential and NO potential and all those things. If we wanted in that context to ask, is there a pollution effect? Then we have a similar issue to what we were just talking about with the height weight data. Namely, to ask, is there a pollution effect, we need to address multiple coefficients. If we looked at a p-value for HC potential and a separate p-value for SO2 potential and a separate p-value for NO potential, suppose we had 3 tests, 3 p-values, and if any one of them was less than 0.05, our strategy was to claim there's a pollution effect. If we do that, we've made an error in the sense that we're trying to answer one scientific question, a single question, is there a pollution effect? But we did it by doing 3 separate tests. So we had 3 ways to incorrectly conclude that there's a pollution effect. Hypothesis testing is intended to be used 1 test per 1 hypothesis. Ideally, you conduct an experiment, you collect your data, and you have a plan from the beginning. This is the model I'm going to fit. This is the test I'm going to do. This is the p-value I'm going to get for asking this question. If instead we come in here and say, well, there's 3 different ways to define pollution, let's test each one of them and claim significance if any of the p-values is big or small, we are increasing our chances of type 1 error. For example, with 3 tests, suppose the null hypothesis is true. There is no pollution effect. If you were to do a single test at significance level 0.05 of that hypothesis, if you did it correctly, then you could say, I expect to make a type 1 error with probability 0.05. But if we're going to do this kind of fishing around analysis where we consider multiple tests of the same hypothesis, the probability of a type 1 error jumps up to 0.14. We would be claiming 0.05 because we compared our p-values to 0.05, but we would be wrong. There's actually greater chance that we make errors whenever you do this multiple testing stuff. So the point of this slide is to reiterate why we need things like likelihood ratio tests and F-tests. The likelihood ratio and F-tests both would be a single test, a single p-value for assessing pollution or height in the height weight example. Let me review here. We are representing our regression models in this compact form, arbitrary regression model. This capital X can do lots of different things depending on what we are trying to do exactly. But we can always represent a regression model in this form, which means we can always compute the estimates of beta using this expression, x transpose x inverse, x transpose y, at least when we have the classical assumptions of IID errors. We can get residuals, and from the residuals we can get an estimate of the residual variability. Call it sigma squared. Then we know what the variances and covariances of the beta estimates are. Sigma squared hat times x transpose x inverse. And we've seen that the diagonal elements of this thing are the variances of the beta coefficients. So their square roots would be estimated standard deviations of the betas. What that means is that we can take regression output and do confidence intervals for the regression coefficients. We've been computing p-values, but confidence intervals are also valuable inferential tools. So suppose we wanted a 95% confidence interval for beta 2. You can construct one as estimate beta 2 and then go plus or minus a t-based cutoff times the SD of beta 2. Estimate plus or minus a cutoff times the standard deviation of the estimate. Suppose you wanted a confidence interval for some linear combination of the betas. What does that mean? I'm going to show you an example in a second here. Hold on. Suppose we wanted a linear combination of the betas. Like back here with this model, suppose we wanted a confidence interval for beta 1 plus beta 3. Suppose we wanted a confidence interval for the slope in height when gender equals 1. If you just wanted a confidence interval for beta 1, you could do beta 1 hat plus or minus a t cutoff times the SD of beta 1 hat. Same thing for beta 3. But how do you do for a combination of them like this? What we can do is represent what we want as a linear combination of the betas. For example, let me come down here and say, in the context of weight height model, yi beta 0 plus beta 1 height, beta 2 gender, beta 3 height times gender. We said that beta 1 plus beta 3 is the slope in height for gender equal 1. Another way to write beta 1 plus beta 3 is 1 times beta 1 plus 0 times beta 2 plus 1 times beta 3 and 0 times beta 0, which can also be written as linear combination. So 0, 1, 0, 1 times beta 0, beta 1, beta 2, beta 3, which we can call some vector of constants V transpose vector of betas. A linear combination of the betas can be written as a constant vector times the beta vector. Then if you wanted a confidence interval for that linear combination, in our case beta 1 plus beta 3, we could do that linear combination of the beta hats, as in estimate, that's the estimate of the linear combination, plus or minus a t critical value, times the standard deviation of that linear combination. And how do we compute the standard deviation of that linear combination? It comes from something we saw earlier. Let me go back to where that was. No, I'm not going to do that. We saw in a previous lecture that if you have a random vector, like we do here, we have the variance of some v transpose beta hat. We saw in a previous lecture that this can be written as v transpose variance of beta hat times v. And we know what the variance of beta hat is. We've already computed that. So if you want a confidence interval for a linear combination of the betas, you can just do estimate plus or minus a t critical value. I'll do alpha over 2 with n minus p degrees of freedom times v transpose variance of beta hat v. Square rooted, actually. I need that square rooted. We are out of time. Let me show you where this comes into play. Like in this model right here. Suppose we had two predictor variables, x and z, and suppose we wanted to test that these two coefficients are equal. Actually, I'm going to get to that next time. In the context of the weight versus height data, there's a sensible reason to ask for an interval for beta 1 plus beta 3, because it is an interpretable quantity. It's the slope and height for g equal 1. And we can get confidence intervals for it using this estimate plus or minus cutoff times standard deviation. It's just that for a linear combination, we have to apply the appropriate v vector. Okay. Pretty sure I didn't explain that perfectly, but we'll talk more about it next time, and I'll show you some more examples. Okay? Any questions real quick? All right. See you Friday.